Students, today we're going to talk about what makes up an atom. What is it? And to get to that, we're going to first define the scope of chemistry. Chemistry is, as you may have heard, the study of matter. Just like biology is the study of life, chemistry is the study of matter. And that means anything that has mass and takes up space. That would be everything around you. Every single thing around you has mass and takes up space. Anything you can touch, anything, even things that you can't touch, all the way down to this very smallest particle we know at the moment is a quark, that's still part of chemistry. And that's part of the domain of what we're studying in this course. Here's a philosophical question for you. Let's say you have a really, really sharp knife and you're really, really skilled at cutting. Is there any limit to how small you could get the substance that you're cutting? Like here is pictured, it looks like a carrot. Let's say you take that carrot and you divide it into small pieces, and then you take those small pieces and divide it to even smaller ones. Is there any limit at which you can't divide any further? Now, as we pose that question, I want you to think about it, and we'll come back to it with the Greek philosopher Democritus in just a moment. We know that the particles that make up all of the matter around us, the smallest we can get that still retains the properties of the substance we're studying is the atom. And atoms are really, really small, almost inconceivably small. Picture this. Planet Earth is about 300 million times bigger than a golf ball. And a golf ball is about 400 million times bigger than an atom. So it's a startling comparison. The difference in size between a golf ball and planet Earth is less than the difference in size between an atom and a golf ball, although they're in the same order, same neck of the woods. So atoms are really, really, really small. Now, back to the Greek philosopher Democritus. Now, in ancient Greece, they weren't doing science the way we understand science. So, Democritus wasn't testing substances in a refutable way. He wasn't publishing his methods and his materials and going about a scientific paper or experiment the way that we would do today. Rather, he was just thinking out loud, maybe with some friends, and he said, if I have a particle, whatever it may be, a piece of wood, and say, let's cut it into a smaller piece. And then I keep cutting and cutting and cutting. And let's say I'm infinitely good at cutting. I have an infinitely sharp knife, and I could, let's say, shrink yourself down to the size of whatever it is you're cutting so that it's not like the material would get so small that your fingertips couldn't handle it. You could shrink yourself and still do the cutting. At least you would maintain that capability in this thought experiment. Well, Democritus says, yeah, there is a limit. There is an absolute limit, no matter how sharp your knife is. And that smallest particle, he coined an atom. An atom in Greek literally means that which cannot be cut. There's the prefix a, which means it's a negative prefix, kind of like un in English. And tom is a root that means a slice or a cut of something. So an atom is literally that which cannot be cut. So in this view of the atom, when you get to the smallest fundamental particle, the view of the atom is just a solid, indivisible, because you can't cut it any further, sphere. And there's nothing inside it. So if it's an atom of wood, let's say in Democritus's thought experiment, then once you get to a point where you can't divide any further, you have an atom of that thing, of the wood. Now, he didn't necessarily know that wood is made up of several different types of atoms, but it was the prevailing idea for many, many centuries. So from thousands of years BC until roughly the 1800s when we expanded upon that idea or poked holes in it. That was what we thought an atom was. Now, we have some direct evidence way back from sophomore year when you studied chemistry. We have direct evidence that there are particles smaller than an atom. Do you remember the sticky tape lab? In that lab, you were to push together two pieces of tape, you were to rip them apart briskly, and upon ripping them apart, you transferred an electron from one tape to another. Now, as to which tape received the electron or which tape lost the electron, it doesn't really matter, and you wouldn't have had any direct evidence of which is which in that lab. But let's say hypothetically in this diagram here, after ripping apart, the top tape now has 4 electrons per atom, whereas it began with 3, and the bottom tape has 2 electrons, whereas it began with 3. So the top tape gained an electron from the bottom tape. Particles that are smaller than an atom do exist, of course, we know about them now, and we call them subatomic, meaning smaller than the atom, which of course goes against the notion of the root, that which cannot be cut. But turns out Democritus wasn't correct. There are particles smaller than the atom, but he was correct in one sense, at least as far as we know right now. Those particles, you might say, well, what makes up the subatomic particles? What we've discovered at this point is there are quarks and leptons, and that make up protons and neutrons. Electrons are kind of like quarks and leptons, similar in size. So they are their own really, really small thing. But in the future, could we discover a particle even smaller than the quark? Well, yeah, potentially. We don't know. The long and short of it is we don't know. So we ask you to think back to your sophomore year science class when we did the sticky tape lab. And what did it show? It showed that we had subatomic particles. Okay, here's a famous experiment that really kicked off the idea that there's something more than a solid indivisible sphere in an atom. The scientist who performed this experiment was J.J. Thomson, and he was experimenting with a setup called a cathode ray tube, in which a stream of particles pass through a hole that travels to a screen that, because of its coating, would be visible in a dark room. And if you just send that stream of particles through the cathode ray tube, the phosphor coating, the screen on the other side of the hole, always lit up right opposite the hole that was cut into a disc that you could subject electric current to. Well, what Thomson did is he said, okay, I notice that when I bring a positively charged sheet of metal near that stream of particles, I can make it deflect in a reliable way. Or if I bring a negatively charged sheet of metal near that stream, I can also make it deflect. And he saw attraction and repulsion, and he said, well, there's got to be some explanation. He says, I think that there's a particle smaller than the atom, and I think that because it's attracted to the positively charged metal plate, that subatomic particle must have had the opposite charge. It must be negative because opposite charges attract. That led him to propose a new model of the atom. Atoms are no longer solid, indivisible spheres, as Democritus proposed. Thomson said the atom is more like plum pudding, which is a British thing that basically just means, think of raisin bread. Raisin bread is dough with raisins stuck in it, and it's baked and it's delicious, especially when you toast it and put butter on it. But it added some complexity to the simple idea of an atom that was suggested by Democritus and was later on adopted by John Dalton, the person who kind of kicked off modern chemistry. Or one, I should say, one of the people who kicked off modern chemistry. In this plum pudding model, J.J. Thomson says, okay, I've got these smaller than atomic size particles. He didn't use the term electron himself. That was used later. But there are these smaller than subatomic particles which are negatively charged. And to make the atom neutral overall, they have to have been stuck into some material, maybe like a dough, that is itself positively charged so that the charges cancel out and it's neutral. Eventually, Thomson proposed these movable charge particles are electrons. And actually, it wasn't he who coined the term electron. It came decades later. One of Thomson's, oh, by the way, Thomson's experiment with the cathode ray tubes came in 1895, so the end of the 19th century. And so there was a huge amount of time between when Democritus proposed a solid indivisible sphere and something more complex than that. Centuries go by. Just 20 years later, in 1911, or 15 years later, roughly, in 1911, one of Thomson's students, Ernest Rutherford, made another huge breakthrough. And the way he came up with this huge breakthrough is by conducting an experiment that's famous. It's called the gold foil experiment. And in this, he gained evidence that there's a solid, dense core to the atom. The way he did this is he took a sheet of metal, like almost like aluminum foil, but it was made of gold. I guess that was the preferred material. And what Rutherford did is he shot small particles called alpha particles directly at this sheet of foil. And as was expected, the vast majority of the particles went straight through and were detected on the other side with a screen, much like the screen that Thomson used. It was a phosphor-coated screen that lit up when a particle was detected by it. But the difference this time is Rutherford did a whole wrapping around screen. So it went all the way from, it went almost a 360-degree screen, and that enabled him to detect particles that didn't just go straight through the foil, but were scattered at significant angles. As he shot particles at the sheet of really thin gold foil, just a couple of atoms thick, a really small number, less than 1%, were actually deflected, and some bounced backwards, which was very, very surprising. The only way that that could happen with consistency is if there were something denser or at least equally dense to the alpha particles being shot at the foil. And Rutherford said, well, that must mean that the atoms in the foil have a dense central core. So if you take a look at the picture on the left, the prediction, if Thomson's plum pudding model were true, is that 100% of the particles would pass straight through the atom. The Rutherford model of the atom proposes that it's not just a lump of positively charged dough, but rather a small positively charged nucleus in the middle of the atom that counteracts the negative charge of the electrons. And it's that small, dense nucleus that did the deflecting of the alpha particles. So less than 1% still were deflected or bounced backward. Vast majority passed straight through, but something had to explain why a small percentage of the shot particles went off at weird angles. So that led us to the Rutherford model of the atom. There's a small, dense central core, which he called the nucleus, where almost all of the atom's mass is concentrated. The vast majority of the atom is empty space. Now, compare the sizes. We're looking at diameters here. Negative exponents being really small numbers. You might remember that from math class. Let's say that an atom is roughly spherical and its diameter is 10 to the negative 8th centimeters. If that's the case, then the size of the nucleus for that atom would have a diameter of roughly 10 to the negative 13th centimeters, on the order of 100,000 times smaller. To put that in comparison, the size of a dot at the middle of a soccer stadium in the middle of the field compared to the size of the entire stadium, where it's a big stadium that can seat thousands and thousands of people. The size of that dot compared to the size of the stadium is about the same difference in size to the nucleus compared to the size of the atom. Isn't that astounding? So the nucleus is very, very small compared to the rest of the atom. In the years following Rutherford's gold foil experiment, scientists notice a lot of interesting things about an atom's mass being roughly, at least for the smaller elements, 2 times the number of protons that it contains. So they were able to count up the number of positively charged particles. And they said something had to account for the missing mass there. And eventually it was in 1932 with a British scientist named James Chadwick that was doing some work with X-ray crystallography. And his discovery, he eventually got evidence for that third particle, that third subatomic particle that had mass but no charge. And he called it the neutron because of its neutral charge. So proton, positive charge, electrons, negatively charged, neutron, neutrally charged. This simple chart really summarizes the major subatomic particles that we're going to be responsible for. And yes, you can get more detailed. Yes, you can get into particle physics here, but that's not something we need to know for this course. For this course, I need you to know that within the nucleus, we have a positively charged proton whose mass is 1, and then we use the unit AMU, atomic mass unit. A neutron has the same mass as a proton. It's also in the nucleus, and it has no charge. It's neutral. And an electron doesn't have a mass of 0. We can't say a mass of 0 because if you remember back to our definition of matter, anything that has mass and takes up space is a particle that is germane to chemistry. Well, an electron, if it didn't have any mass, wouldn't be matter. Well, it does, turns out it does have a mass. It is almost 1/2000th the size of a proton or a neutron. Specifically 1/1836th of an AMU. And the specific location we'll kind of nail down later. There's a lot to that, but all I want you to know for now is that the electron is negatively charged, has a really small mass, almost 0, but not 0, and it's located outside the nucleus. Have you ever heard of subatomic particles besides proton, neutron, electron? I mentioned this before. There are even smaller particles, quarks, that make up the protons, leptons, gluons, muons. You may have heard the term Higgs boson, also known as the God particle, which is thought to confer gravitational gravity to a piece of matter. So that's outside of our field of study, but it is smaller particles yet. Okay, some other really, really important models, just to mention briefly. Niels Bohr was a Danish chemist who said something about the location of the electrons. So he said, total agreement that protons and neutrons are inside the nucleus, protons are positive, neutrons are negative, electrons are outside the nucleus and negatively charged. Niels Bohr said the electrons circle the nucleus in rings that are concentric, meaning they have the same center. So and Niels Bohr, even though this isn't the most accurate description of the position of electrons, it is really, really helpful. And we're going to lean on the Bohr model in some future lessons. But just like planets orbit the sun, in fact, there was a bit of a fascination, an obsession even, with the symmetry between the hugest structure known at the time, the solar system, with planets orbiting the sun, and the smallest system known at the time, the atom, with the electrons orbiting the nucleus. And they thought, oh, isn't it funny how the biggest thing and the smallest thing looks kind of similar? They must behave the same way. It turns out that's not the case, but it is really, really helpful. And lastly, and the most up-to-date model of the atom is something of, they call it an electron cloud. It means that we can't actually know where an electron is. We can't know its location and its momentum at the same time. By the time the electron has given off some way of detecting where it is. It's moved on to a new location, and we can't know where that new location is. So thus, what we can do is calculate the likelihood of finding an electron in a given region of space. That's the cloud. And so we're only calculating a probability. And you have to define like, oh, are you going to make your edge of your region of space 90% higher likelihood of finding an electron, 80% or higher, 70% or higher? Um, and anyway, that's something that is we'll revisit later. It's called the electron cloud model. Okay, I leave you with one last question here. Back in ancient Greece, Democritus proposed that there is a limit to smallness. He said that atoms are solid, indivisible spheres. Thousands of years go by, and in 1895, J.J. Thomson proposed that there are negatively charged electrons within the atom, and those negatively charged electrons are stuck into a lump of positively charged dough. This is called the plum pudding model. Just 15 or so years later, Ernest Rutherford discovers evidence that there is a dense core to the atom, which he called the nucleus. That's where the positive charge is, and the rest of the atom, if it's not an electron, it's empty space. Furthermore, the nucleus is 100,000 times smaller than the atom itself. It was only about 20 or 30 years after Rutherford that Niels Bohr proposed that electrons circle the nucleus just like planets circle the sun. And it was only about 10 years after Bohr proposed his model that the evidence of using quantum mechanics that the electron cloud model was proposed. So there's been a ton of progress recently, seeming to increase in speed. So number one, our progress has been amazing. And number two, is there some new model of the atom that you can discover? Will you carry on this progress in chemistry? I hope so.